So when I talk about equilibrium of a rigid body, I'm talking about mechanical equilibrium. And mechanical equilibrium will be there when there will be translational equilibrium and rotational equilibrium. Translational equilibrium we have already studied. Okay. Means on page number 99 in NCERT there is a topic equilibrium of a particle. So for translation equilibrium, I want net external force acting on the particle, acting on the body. So here we are talking about rigid body, there we were talking about particle. So the net external force acting on the rigid body must be 0. Okay. So students, whenever we talk about vectors, so it means the x component of the force must be 0, y must be 0 and z must be 0. So that's the meaning of so all the three components of force must be 0, means sigma fx must be 0, similarly sigma fy must be 0, and sigma fz must be 0. Means the forces along the x-axis, forces along the y-axis and forces along the z-axis, the net resultant should be 0. This is what is the meaning of net external force equals to 0. So students, whenever we talk about any vector, so we are writing here 0, it means all the three components of force are 0. Okay. So we can further write it as that fx, if this is 0 means fx plus fy plus fz is equals to 0. So means you can write it as 0 I cap plus 0 j cap plus 0 k cap or 0 and miss. So for you need to remember and understand this thing for all the vectors, that whenever I'm talking about that particular vector as 0, so it means all the three components along all the three directions are 0 separately. Okay, separately. Okay. So the forces change the translation state of the motion of a rigid body. So what do these forces do? So forces, they change the translational state. Okay, and ultimately they change the linear momentum. Now what the torque changes? Torque changes the, so force changes the translational state, whereas torque changes the rotational state of the motion of the body. Means it changes the angular momentum of the body. So whenever you apply force, you know the formula, Newton's second law, F is equals to dP by dt, and here torque is equals to rate of change of angular momentum, right? dl by dt. Okay. Now if I talk about mechanical equilibrium, it means I'm not changing the means my net force is 0. So it means, so if this F is equals to 0, so F can only be 0 when P is constant, P is conserved. Okay, because this is equals to 0 means what? P is constant, because derivative of only a constant can be 0. Okay, so this is 0 means P is constant. Okay, P is conserved, and if this equals to 0, it means L is constant. So then only we will say that so this is the condition for translational equilibrium, and this is the condition for rotational equilibrium. So here P is conserved. Here means linear momentum is conserved in case of translational equilibrium. Here angular momentum is conserved. Angular momentum is constant. Okay. So that's what is written over here, that rigid body is said to be in mechanical equilibrium if both linear momentum and angular momentum are constant. So then only their derivatives will be zero. So
Excuse me, sir.
yes.
Sir, what is translational state?
Translational state. Okay. So see, we have let me discuss if you want to know translational state. See, there are a lot of kinds of motion. You are also studying periodic motion also. Okay, but in mechanics we deal with normally this kind of motion. So first is we started in chapter 3, that is rectilinear motion, which is motion along a straight line, and then in the next chapter motion in a plane we studied, and the means uniform circular motion also, and then we have pure translational motion. So this is what we have studied in this chapter: pure translational, pure rotational, so pure rotational motion and rolling motion, which is a combination of translation as well as rotational. So what is translation motion? You can see we have two figures of translation motion. So in figure 7.1 you can see that this box is clearly it is sliding down. So velocity of all the particles of the body. So I have taken only two particles, P1 and P2. So there are n number of particles. So all the particles of the body have same velocity at a particular instant. So this is what a translation motion is. So whenever the word translation motion comes, translation motion means pure translation motion, and at any instant of time all the particles of the body have same velocity. So here also you can see means here that's the direction of the velocity, means this flask, it is this vase or whatever it is, so it is coming down. So all the particles have same velocity at a particular instant. Here the velocity here and here is different, okay, but at a particular instant the velocities are same, their magnitude as well as direction. In pure translational motion, in pure rotational motion, we have every particle of the body moves in a circle, and that circle lies in a plane perpendicular to the axis of the rotation, and the center of the circle also lies on the axis. So in pure translation motion, at any instant, here we have all particles of the body have same angular velocity. So here we have same angular velocity in pure rotational at any particular point of time, whereas they have different linear velocities, but angular velocity is same. We know that the linear velocity of the particles which are at the outer edges, they have more, and whereas near to the axis the linear velocity is less in magnitude, okay. But so in translation motion, same linear velocity at any particular instant of all the particles, and here we have same angular velocity. Now if we look at the rolling motion, so rolling motion on the surface, so this ball is rolling down the surface. So this is the rolling motion of the cylinder, and you can see different velocities, and the velocity of P3, which is in contact, is 0. There is no velocity vector over here. So they have so it is not pure translational, it is translational as well as rotational. So translation means simply the position here is changed, but in pure translational, when the word pure comes, then the velocity of all the particles will be same. So it is not pure translational, it is translational and rotational, this motion. And this is also the combination. This is not the rolling motion, but this is a example of a combination of translational and rotational. So this was pure translational. The flask was vertical, but here you can see that this object is also rotating. Okay?
Yes, sir.
Okay. So these were the different kinds of motion of a rigid body. So now if we look at the equilibrium part that we were studying. So means so the condition for the translational equilibrium, net forces must be zero. Separately they must be zero along the x-axis and along the y-axis and along the z-axis. And for rotational equilibrium, similarly, we have the net torque must be zero. So net torque must be zero means along the x-axis net torque must be zero, along the y-axis and along the z-axis separately it must be zero. Now let us look at this figure 7.20 which is there in your book. So which page number is it?
159.
Yes, it is 159. So you can see that let us read it from the book. Okay, there is one more thing. There can be partial equilibrium also. Partial equilibrium. So what is partial equilibrium? Partial equilibrium means when there is translational equilibrium but not rotational, or when there is rotational but not translational. Okay? So when there is one of the equilibrium, either translational or rotational, then the equilibrium is partial. So partial means either translational equilibrium or rotational equilibrium. So if both the equilibrium are there, then it's we only say equilibrium or we say mechanical equilibrium. But if one of the two equilibriums, then it is partial equilibrium. So now let us read from the book. Mansi, you can read from here that consider a light. Just the paragraph above the figure.
Consider a light that is of a negligible mass, rod AB, as shown in the figure. At the two ends A and B, of which two parallel forces, both equal in magnitude and acting along same direction, are applied perpendicular to the rod.
So you can see, put your fingers at point A. So this is A and this is B. So these are the two ends of the rod, and this rod, all the rods that we will be taking in this chapter, they have negligible mass. So we are like strings, we have taken the string with negligible mass. Similarly this rod is also of negligible mass, and two forces. So these are the parallel forces. They are equal forces, you can say. Okay, so equal in magnitude and same direction. So these are applied perpendicular to the rod. So the angle here is this force is also, this angle is 90 degree with the rod, and this angle is also 90 degree with the rod. Okay. Let's see with the yes.
Let C be the midpoint of the AB. CA equals to CB equals to A. The moment of the force at A and B will both be equal in the magnitude AF but opposite in sense as shown.
Okay,
The
so
net
students, whenever this word moment comes, it means we are talking about torque. We are talking about rotational motion. So we are talking about torque. So whenever this word moment comes, so moment of forces means torque. Okay, and At some of the places we only use the word moment. So moment of forces, and some of the time using the moment. So we are talking about torque at that point of time. Is this clear?
Yes, sir.
Okay, good. Yes. So have you understood this concept? That the system will be in rotational equilibrium but not in translational equilibrium. Okay. So how is it? You can see that. Let us find out the net force, means what the force acting on it and what is the torque. Okay. So see here, force we can clearly see. We need not to calculate. We can clearly see this is a force. If downward direction, I'm taking this this as x-axis, positive x-axis, and this is positive y-axis. So the downward will be negative, right? So minus f. So I'm taking this force as minus f, and this also minus f downward. So the net force is 2f. So students, when there are only means two directions possible, upward and downward. See here in this equilibrium of a rigid body, just keep in mind two simple things about directions, that we need not to write the forces and torque in vector form. Okay, we'll simply write like in rectilinear motion, one direction is positive and one direction is negative. So like positive velocity and negative velocity. Similarly here, negative 4, that means this direction is negative, so minus f, and this also minus f. So both the forces are in same direction, so minus f plus minus f is minus 2f. So that's the net resultant force act on this. So this rod will move downwards. Okay, so the rod will somehow, it will reach at this point after some time. So all the particles, so translational motion is there. So translational motion means this rod is moving downwards with all the particles of the rod moving with the same velocity. Okay, now so that's the net force. So we have translational motion. Body is moving downwards. I've told you that it will reach here, AB. Now what about the torque acting on it? So what is the formula for the torque? Torque is equals to, we know that torque is equals to R cross F, right? And that's equals to, so if I talk about magnitude only, that is RF sine theta, or I can write it simply R perpendicular into F. Okay, so what is the theta here? Theta is 90 degree. Okay, so theta is 90 degree, sine 90 is 1. So tau will be equals to R into F. So theta is 90 degrees, sine 90 is 1, so tau will be equals to R into F. Now what about the direction? This is the magnitude RF. What about the direction? If it is moving in the anti-clockwise direction, like angle theta, remember, I am moving in the anti-clockwise direction, I was taking the theta as positive, and in anti-clockwise direction I was taking the theta as negative. So similarly the case here. So the if the torque is if it is rotating in the anti-clockwise direction, I will if this torque is responsible for the motion in anti-clockwise direction, I will take the torque positive, and I will take the torque negative if it is responsible for moving this rod in clockwise direction. Okay, so you can write anti-clockwise moments are taken to be positive, and clockwise moments are taken to be negative. So clockwise moments positive, and anti-clockwise movements, or you can say counterclockwise movements, are taken to be negative. So these are the sign conventions that we are taking by our own. Okay, so there are only two directions, so we need not to use the vector sign here. Okay, so you can see that this force is acting downwards, so obviously the torque, the resultant torque, the resultant will be in the anti-clockwise direction. Agreed, all of you?
सर मेरे को तो यही समझ में नहीं आया कि रोड घूम कैसे रही है.
बहुत अच्छा क्वेश्चन है. ये जो रॉड है, ये जो सी है, ये इसका, ये जो रॉड है टॉप, ये आप जो है अपना पेन होल्ड करो हॉरिजॉन्टली, ठीक है?
यस सर.
हॉरिजॉन्टली होल्ड कर लिया. अब उसको नीचे लाओ, दोनों तरफ से पकड़ लो उसको, दोनों हैंड से, राइट हैंड और लेफ्ट हैंड दोनों हैंड से पकड़ लो और उसको नीचे लाओ दोनों हाथों से. आप नीचे फोर्स लगा रहे हो ना? यस.
बट सर ये कर्व्ड एरो जो इनके नीचे लगी हुई है, ये क्या है फिर?
हाँ, ये जो कर्व्ड एरो है, इसमें दो चीजें हैं ना, एक तो फोर्स और एक टॉर्क. हम टॉर्क कैलकुलेट कर रहे हैं कि ए पॉइंट पर कितनी टॉर्क लग रही है. आप बी पे मत लगाओ, आप जो फोर्स है वो बी पे मत लगाओ. तो क्या होगा, आप सिर्फ ए पे लगा रहे हो तो ए नीचे आएगा नहीं आएगा, है ना? तो ए पे, ए जो है आप यहाँ फोर्स मत लगाओ, आप जो है ना बी जो है इसमें सपोज दोनों में से एक जगह फोर्स नहीं लगाओगे तो वो जो रोड रोटेट होना शुरू हो जाएगी. यहाँ पर क्या है, ए पर आप, ए पे जो फोर्स लग रही है that is this, it will rotate it in this direction एंटी क्लॉकवाइज. तो that is positive AF. टॉर्क जो लग रही है, टॉर्क का फार्मूला क्या है, RF sin थीटा. sin थीटा इज 90 डिग्री. तो कितना टॉर्क लग रहा है इसके ऊपर, ए पॉइंट के ऊपर? किसी पॉइंट के ऊपर अगर फोर्स लग रही है तो टॉर्क भी लग रहा है. किसी पॉइंट के ऊपर टॉर्क है ना, टॉर्क इज इक्वल टू आर क्रॉस एफ. आर जो है वो ओरिजिन से उस पॉइंट का पोजीशन वेक्टर है जिस पर आपकी फोर्स लग रही है. टॉर्क कैलकुलेट कर सकते हो ना आप इस पॉइंट पे, टॉर्क एट ए.
यस सर.
तो इसमें क्या दिक्कत है, टॉर्क एट ए. आप भूल जाओ रोटेशनल मोशन, ये वो सब कुछ भूल जाओ. आप मुझे बताओ ए पे टॉर्क कितनी लग रही है. सिंपल फार्मूला आपके पास है, पोजीशन वेक्टर इनटू क्रॉस फोर्स एक्टिंग ऑन दैट पॉइंट, और उसको हम लिखेंगे टाउ इज इक्वल्स टू आर एफ साइन थीटा, उसका मैग्नीट्यूड. तो आर एफ साइन थीटा 90 डिग्री है, तो कितना लग गया, आर इंटू एफ. आर किसके इक्वल है यहाँ, ए के इक्वल, राइट? दिस इज योर ओरिजिन, यू आर कंसिडरिंग दिस एज ओरिजिन, दिस सेंटर. तो यहाँ से आप डिस्टेंस, तो दैट इज योर आर. तो आर इज इक्वल टू ए. तो परपेंडिकुलर डिस्टेंस भी इसमें यही है. दिस इज योर, ये क्या है इसमें, व्हाट इज दिस लाइन, व्हाट डू यू कॉल दिस लाइन? यस,
लाइन ऑफ एक्शन.
लाइन ऑफ एक्शन. लाइन ऑफ एक्शन. तो लाइन ऑफ एक्शन को आप इस पॉइंट से परपेंडिकुलर डाल दो लाइन ऑफ एक्शन पे, दैट इज अ परपेंडिकुलर डिस्टेंस. तो परपेंडिकुलर डिस्टेंस ए वो सेम ही होता है जब कितना होता है थीटा 90 डिग्री. ओके, गॉट इट. तो यहाँ पर कितना टॉर्क आ गया, प्लस ए एफ. बस ये ध्यान रखना, ये जो है. और यहाँ कितना टॉर्क आ गया, ये यहाँ से किस तरफ मूव होगा, आप इसको दबाओगे इसको, तो ये किस तरफ आएगा, नीचे ही तो आएगा. ये बी जो है, अगर आप इसको नीचे खींच रहे हो, आप जो है एज्यूम करो कि ये एक बैलेंस है, समझ रहे हैं? तराजू होती है ना, तराजू, पहले पुरानी तराजू होती थी.
हाँ सर.
यस सर.
पुरानी तराजू होती थी ना, तो उसमें दोनों तरफ जो है आप मासेस रखते थे, ठीक है? और तो इसमें क्या है, अगर आप दोनों तरफ इक्वल मास रख दोगे, ये फोर्स क्या है, फोर्स ग्रेविटेशनल फोर्स है. सपोज आपने दोनों तरफ मास रख दिया, ठीक है ना, और ऊपर से कोई पकड़ेगा नहीं उसको, तो धड़ाम से नीचे आएगी नहीं आएगी? ऊपर से तो किसी ने पकड़ नहीं रखा, ऊपर तो कोई फोर्स लगी नहीं रही. ये क्या सिचुएशन है, आपके पास जो है एक बैलेंस है, समझ रहे हैं, और दो मासेस रख रखे हैं बैलेंस में आपने, सेम मासेस, और पहले आपने ऊपर से पकड़ रखा था उसको, अब आपने उसको छोड़ दिया तो ऊपर तो फोर्स लग नहीं रही, जब उसको एयर में छोड़ दिया तो दोनों फोर्सेस कहाँ लग रही हैं, नीचे, तो तराजू कहाँ जाएगी, गोल गोल घूमेगी या सीधी नीचे आएगी ग्राउंड पे,
सीधी नीचे आएगी सर।
तो वही एग्जाम्पल है ये कि वो तराजू जो है वो बिल्कुल सीधी नीचे आएगी, तो कौन सा मोशन होगा फिर,
ट्रांसलेशनल।
बात आई समझ में। अब आप क्या करो, अब आप फिगर बी देखो, अब आपने क्या कर दिया, एक में जो है वो जो मास है वो सपोज आपने कर दिया कम और दूसरे में कर दिया ज़्यादा, अब एक में 2 kg मास रख दो, एक में 1 kg मास रख दो, तो क्या होगा, वो कहाँ जाएगी वो तराजू, बताओ। जब ये थी ना आपकी, और यहां पर आपने जो है यहां से आपने उसको फिक्स कर दिया, जैसे आपका जब आप शॉप पे जाते हो तो यहाँ बीच में होती है ना ये ऐसे, ये है ना, निडल इज देयर इन द मिडल। अब आपने यहाँ रख दिया 2 kg और यहाँ रख दिया 1 kg, तो दिस बैलेंस, ये बैलेंस कहाँ जाएगा, ये 2 kg है तो नीचे जाएगा ना, यहाँ फोर्स लग रही है 2 × 10 20 न्यूटन, और यहाँ लग रही है कितनी 10 न्यूटन सिर्फ नीचे, है ना, तो क्या होगा, ये पार्ट नीचे चला जाएगा, ये पार्ट ऊपर चला जाएगा, ऐसे हो जाएगी ना तराजू, ऐसे हो जाएगी ना, ये जो 20 वाला ये जो है जो 2 kg ये नीचे जाएगा क्या ये पार्ट।
हाँ सर आ गया मेरे को समझ में।
तो दिस इज द वे, तो रोटेशनल मोशन होगा, अगर ये दोनों फोर्सेस इक्वल नहीं है तो देन देयर विल बी रोटेशनल मोशन। ओके, तो बस ये तराजू से समझो इसको, ये अच्छा पॉइंट है, ये तराजू से समझ सकते हो इसको, गॉट इट। तो बैलेंस, हाँ बैलेंस से समझ लो इसको, बैलेंस जो पुरानी जो तराजू होती थी, पुराने जो ओल्ड बैलेंस होते थे हमारे पास, वो कोई देखा होगा आपने, तो इट इज समथिंग लाइक दैट। तो चलो लेट अस लुक एट दिस फिगर। अब अब एक ये पर्टिकुलर केस है, ये तो मैंने लिया था 2 kg 1 kg एक जनरल केस था, अब एक ये पर्टिकुलर केस है, स्पेशल केस, और इस स्पेशल केस में क्या हो रहा है, आप अपने पेन को होल्ड कर लो, जो मैंने पहले कहा था, पहले तो आप ए और बी दोनों पे फोर्स कहाँ लगा रहे थे, इक्वल फोर्स नीचे, 2 फिंगर से आपने पकड़ा था और उसको कहाँ लेकर आ रहे थे, ऊपर से नीचे, राइट। नाउ व्हाट यू आर डूइंग, ए पे नीचे वर्टिकल फोर्स लगा और बी पे वर्टिकल अपवर्ड, तो बताना क्या हो रहा है आपके साथ, पेन पे क्या हो रहा है, पेन को
रोटेशन,
हाँ पहले पेन को होल्ड इट हॉरिजॉन्टली होल्ड किया, अब लेफ्ट साइड पे फिंगर से उसको पकड़ो और लेफ्ट साइड से नीचे फोर्स लगाओ, और राइट साइड से ऊपर फोर्स लगाओ, तो क्या होगा। तो ये जो दोनों जो फिगर्स हैं, मुझे उनका डेमो कौन करके दिखाएगा एक बार फटाफट। मानसी आप ट्राई करोगे।
ओके सर, लेट मी ट्राई।
हाँ यस, वेरी गुड यस, थोड़ा सा हाँ कैमरे में वी आर अनेबल, यस नाउ इट्स ओके गुड। हाँ शो मी द पेंसिल, यस, और पेन वट एवर इट इज, हाँ ओके। सो सिंपली यू हैव टू apply downward forces at both the ends, so it will come, yes, yes, bring it down, yes, from both the ends, first figure, yes, so you are applying the force, downward force at both the ends, so it will now what about figure B, on one end you are applying downward force, on other end you are applying upward force, yes, what will happen, very good. So now there is a translational motion, But is there, oh sorry, there is a rotational motion. Is there any translational motion? No. Okay, there is only, yes, rotated, yes, upward and downward force. So this is, the force are equal and opposite. So very good, thank you, Mansi. So this is a special case when we have equal and opposite forces. Students, this is very important concept, couple, very important. It is one of the ABCDs of physics. So understand it clearly. First thing, in the couple, what I want equal and opposite forces at two ends. Okay, even if they are not at two ends, still it's okay. But the second thing is that they are not supposed to be along the same line of action. Line of action must be different, then only there will be rotation motion. Is this clear? If suppose I am applying the force over here and then one force, equal and opposite forces, but they are along the same line of action, so there will be no rotational motion, couple will not be formed. Okay, so couple will only be formed when there is equal and opposite forces along different lines of action. So in this case, couple will not be formed. Is this concept clear to everyone? So what's a couple? Or you can say simply torque. So what's a couple? So couple is a pair of forces of equal magnitude but acting in opposite directions with different lines of action. So friends, this is very important, most important concept. And a couple produces rotational motion without translational motion. So let us now calculate how much the force acting on it. So downward force acting on it is that we are considering at minus F, and upward is plus F. So the net force is 0. So there is a translational equilibrium. So now let us calculate the torque. So torque here is, you can see that you are pressing it downward, so there will be rotational motion in the anti-clockwise direction, and here also you are pulling it up, so there will again be direction in anti-clockwise motion. So here also anti-clockwise positive, here also anti-clockwise positive. So both the torque are positive, and magnitude is, the angle is here the angle is 90 degree, here also the angle is 90 degree, so sin 90. So we got plus AF and plus F. So that is net. So total torque acting on it is, so net force is 0 but total torque is 2AF. So it results into rotational motion. So now, like, this is the same thing as you open the cap of a bottle. So how do you open the cap of a bottle? Yes, how do you open the cap of a bottle? You can open it with one finger also. With one finger also you can open, but it's comfortable if you open with both the one finger and one thumb. Yes, you use index finger and thumb to open the cap of the bottle. So this is the cap of the bottle, right? So you apply, to open it, you apply force in this direction, and from one so like from thumb you are applying force in this direction, and from index finger you are applying force in this direction. This is what you does. Yes or no?
Yes, sir.
Yes, sir. Yes, sir.
So when you do this, the there will be rotational motion. So this is the so that's the case of the couple. So means equal and opposite forces along different lines of action. So we get a couple. Got it? Any doubt? Okay. Now let us do one example based on it. So next topic is principle of moments. So what is principle of moments? So principle of moment is like, see here, now I have placed this support over here. Okay, this is a rod and I have placed a, you can see a support over here. This is just like your seesaw. You know, the students, means they sit at both the ends, right? It is just like seesaw. So see, this is called support. Okay, this is the support that I am providing. And see student, this point, this point, I'm talking about this point where this support is touching the touching this lever or touching this rod. So that point is known as fulcrum. Okay, so support is an object, whereas fulcrum is a point. Okay, so this is your rod or lever, whatever you say. Have you got this figure? Yes.
Yes, sir.
So this is your support. This is just like seesaw. Okay, and two students. So what you do? You use the lever. This is the lever, and this is the load you have on one point. Actually, what you are doing? You have a load at this point. You want to pick this stone. Okay, this is the stone, heavy stone. You can call it load. You want to pick this stone. So what you will do? To pick this up, you will apply the force downwards. You will press it downward. This side of the lever. Yes or no?
Yes, sir.
Yes. So this is what you do. So this distance, which is from the from fulcrum to this load, this distance is load arm. So it's so simple. So it has two arms. This fulcrum divides the lever in two parts. One is load arm, the one which is towards the load, and the another one which is towards, so you are putting the efforts downwards. So the another is effort arm. So this length is effort arm. Okay, so simple. You want to lift this load? You want to lift the load? So that side is load arm and the another is effort arm. So this load arm is D1, this length, and this is D2. So D1 plus D2 is the total length of the lever. So AB lever is D1 plus D2. Okay, and this ideal lever, so ideal lever means this rod has negligible mass. So D1 and D2 you have understood. So suppose this stone, it has mass M. So what is the force acting downward? That is mg. Okay, so that is your, so D1, so the force is F1, and this force is the effort that you are putting in. So you are applying downward force so that it will go up. Okay, so this force must be greater, your effort must be greater, then only the force will be picked up. So obviously F2. So but some of the students, what is the force here? It will be considered, your effort is considered as F2. Okay, so this is a very simple figure. This is your support and this is your load that you want to pick up. Okay, load to pick up. So you are putting efforts to lift the load. Is this clear to everyone? So what is principle of moments? Principle of moment is so simple. D1 into F1 is equals to D2 into F2. Okay, F1 D1 is equals to F2 D2. Is this clear? This formula, this equation, so simple equation.
Yes, sir.
What do you want, students? You want to apply more force or you want to apply less force?
Less
Yes.
force.
Yes, you want to apply less force. So what you can see, force is you cannot change F1. F1 is not in your hands. Okay, So you have what you want. You want to pick a heavy stone with less effort. This is what you want. Yes, you want to pick up a heavy stone with less effort. So for that, what do you need? This is d1 f1 equals to d2 f2. So if you increase d2 here, what will happen? Suppose this is 4 into 6. This is also 4 into 6. Suppose this is in the middle. We are in the middle and we are applying equal force. And suppose here so I want now heavier stone. So I want 12 kg stone. Okay, means the 12 Newton force it is applying. So instead of 6 Newton, this is your load side. This is your load arm, and this is the effort that you are putting in, and this is your effort arm. Okay, so 6 Newton. Okay, both the kids are sitting on the both sides with equal masses, so it will remain in the middle. Now the load is 12 Newton. You want to pick 12 Newton. So what you need to do? You need to change the position of the support. So make the load arm 2. Make the load arm equals to 2. So this will become total is 8. So this will become 6 into, you are applying the same effort. Okay, so this is 24 Newton and this is 36 Newton. So obviously this is greater, so it will be picked up. Have you understood this simple concept? You can clearly see in this figure also. So load arm should be this load arm, this is in meters, so this must be lesser, and your effort arm must be greater, and that's what we call mechanical advantage. So what is mechanical advantage? Mechanical advantage is your d2 by d1. And d2 by d1, what is d2 by d1 according to this formula? So f2 will come this side, so f2 by f1, f1 by f2. See, that's equals to d2 by d1, or you can say even f1 by f2 is equals to, so d1 will come this side, d2 by d1. So d2 by d1 you want, and that's equals to f1 by f2. So this mechanical advantage, this d2 must be greater. You can see that this is your the d1 is 2 meters and d2 is 6 meters, right? So but here this if you want means here definitely if this much thing will be there will be acceleration, means it will be accelerating, this part will go up with acceleration. But if you want it to go slowly, you want to pick the load slowly, so obviously both of them must be equal, so that the initial efforts that you are putting in, so once it start, it will keep on moving up. So without acceleration you want, so here you can pick the load up to means 36, so 18 Newton. You can pick the load up to 18 Newton. So both sides will be 36. So see, you can pick 3 times the load. So here the mechanical advantage is how much? D2 by D1 is, you can check 6 meters upon 2 meters, and from here also 80 Newton upon 6 Newton. So mechanical advantage, it has no units because this units gets cancelled out, and mechanical advantage is 3. So you want the mechanical advantage to be greater than 1. What do you want? You want the mechanical advantage to be greater than 1. Yes. So you want effort arm to be greater so that F2 is lesser. You want D1 to be lesser so that F2 will be greater. Yes. So have you understood this concept, students?
Yes, sir.
Because the product of these two quantities D2 and F2 is equal to the product F1 D1. So you want F2 to be lesser. So कहानी यहाँ से start होती है. आप चाहते हैं F2 कम हो. F2 कम हो तो product तो वही same होगा. तो you need to increase D2. So if you want lesser F2, if you want to put lesser effort, you need length of D2 to be greater, so that D1 will be lesser. और तो आप इस सपोर्ट को जितना इस तरफ मूव करते जाएंगे उतना ही आपका एफर्ट कम होता चला जाएगा. ओके. तो आपने देखा होगा कि हम ऐसे सपोर्ट देके लीवर से हम पिक करते भी हैं. इफ यू हैव सीन, इफ यू हैव डन, अदरवाइज यू कैन डू इट. स्टूडेंट्स, इज दिस कंसेप्ट क्लियर? सो फ्रॉम प्रिंसिपल ऑफ मोमेंट वी गेट मैकेनिकल एडवांटेज, एंड मैकेनिकल एडवांटेज नथिंग बट इस D1 को इधर ले आओ और F2 को इधर ले आओ. सो दैट इज F1 upon F2, and that is equals to D1 upon D2. So this is what this concept is all about.
सर,
Yes.
हमें सपोर्ट को हमारे लोड आर्म मतलब पॉइंट ए के ही नीचे ले आते हैं, तब तो हमको कोई एफर्ट लगाना ही नहीं पड़ेगा.
नहीं, वो तो जीरो हो जाएगा. फिर सपोर्ट को एग्जैक्टली उसके नीचे ले आओगे तो, है ना. थोड़ा सा होना चाहिए, थोड़ा सा. लोड आर्म जितनी कम होगी उतना बेटर है. जितनी लोड आर्म कम है उतना बेटर है. ओके. तो जितना आप नजदीक ले जा सकते हो ले जाओ. अगर लोड आर्म आपने जीरो कर दी, है ना, तो क्या होगा?
तो वो हमारा ऑब्जेक्ट हमेशा ऊपर ही रहेगा.
हाँ, ये जो है, ये दिस इज D2. दैट्स ए गुड क्वेश्चन. सो दिस इज D2 बाय D1. अरे भाई ऐसा हो जाएगा ना. ये F2 को यहाँ ले आओ तो D1 कहाँ जाएगा? इधर नहीं आएगा, नीचे. तो यू आर टेलिंग मी कि यू आर मेकिंग D1 इक्वल्स टू 0. सो मैकेनिकल एडवांटेज sort of infinite, you will have mechanical advantage. Okay. So but so that's not means practically you need the D1 to be as lesser as possible. Okay. If it tends to 0, then mechanical advantage will tends to infinity. So the main thing is we want it to be greater than 1. Then only lesser effort. So that is why we use lever. We want to put less effort and we want to put more load. So load arm should be means lesser the load arm, lesser will be the effort to pick up the load. Is this clear to everyone?
Yes, sir.
Excuse me, sir.
Yes.
So what's that R there?
What's the R? Sorry.
Yes, sir.
Where is R?
So in figure 7.23.
Oh yes.
Above the
yes, sir. But
it's
R.
there.
Very good. Good question. See, if there is support, then at this point, there will be the reaction also. See, this rod is although this rod is negligible, but this as the forces are acting on both the points, so definitely this means it will, if I don't have the support, it will come down. There will be translational motion also. This rod, if there is no support, both the forces are acting downwards, so it will come down. Yes, like figure A we did 7.22A.
So but here we have fixed the support now. So
7.20a. If you remove this support, this will become the figure 7.20a that we did earlier. If you have no support, then this will be the figure. Yes, see, this figure and this figure has only one difference. We have a support over here. This has no support, so there will be translational motion. Okay, so what this support is doing, this support is preventing the rotational, preventing the translational motion. Let us find the forces. See this R. See, like you have this table and you have placed your book on this table. Okay, this is your book that you have placed on this table. Okay, this is a block you have placed on this table. So this block, is this block moving? No. Why? There is gravitational force acting on it.
Normal reaction.
Yes. So that's the normal reaction. So equal and opposite forces applied by the table on the, so that is Newton's third law. So this is the force F1 applied by this block downwards on the table, and this is the force F2, which is your reaction, normal reaction, or you can say simply reaction. So R or N, whatever we say. And here F1 is equals to minus F2. So then only the forces are equal, and then only there will be equilibrium, translational equilibrium. Yes. Got it? See,
Yes, sir. Means
R is the reaction of the support at the fulcrum. R is the reaction.
sir, then R is providing translational equilibrium there.
See, there are both the equilibrium. The one thing is given that I have not told you yet. What is given thing here? The given thing is mechanical equilibrium. What is given thing? Mechanical equilibrium. So there will be both the equilibrium, translational and rotational. So for translation motion, I want sigma. So here no force acting in x direction, no force acting in z direction, there is only force acting in y direction. So sigma Fy is 0. Okay, sigma Fy is 0. So translational equilibrium. Rotational equilibrium, sigma tau equals to 0. Okay, so tau, if we are considering this x-axis, y-axis, then the tau will be in z-axis, perpendicular to R and F, right? So tau will be in which direction? Z. Yes?
Yes, sir.
So here sigma Fx is also 0 and sigma Fy is also 0. And rotational tau Z is equals to 0. So now if there is, the given condition is translational equilibrium. So translational equilibrium can only be there when there is sigma Fx is equals to 0, sigma Fy equals to 0, and sigma Fz is equals to 0. See, so Fy, there is no force given. Fx, no force is given in x direction, no force is given in z direction. So the only force which is given is in y direction. So we have two forces. So their sum must be 0. So it means, let us find their sum. So this R in upward direction, so I am taking it positive. Okay, and this F1 is in negative direction, F2 is also in negative direction. So minus F1 and minus F2. So the net will be 0. Sigma Fy is equals to 0. So the magnitude of the net force is 0. Is this clear?
sir.
Now rotational equilibrium is there. So rotational equilibrium, the torque acting at this point A, R into F, because this angle is 90, so R into F, and this direction is positive. So plus D1 F1, and this direction is negative, so minus D2 F2. Okay, same as this figure, same as the above figure. The only difference between these two figures is this R, this due to this support. That is the only difference. Okay, so due to that difference we have this R over here. If there is no R, then the net force will be minus 2F if the forces are equal. Yes? And here also it was plus AF minus AF. So plus D1 F1 plus D2 F2, because D1 F1 is equals to D2. So as a result from here, because there is rotational equilibrium, so as a result, what do we get? We get D1 F1 is equals to D2 F2. So this is the relation we have derived. So this is the derivation of so derive this principle of moment. So this is the derivation. Of formula D1 F1 is equals to D2 F2. This is the derivation of this one. Okay. See, translational equilibrium, sigma Fy is equals to 0. Rotational equilibrium, net torque is 0. Okay.
So I'm not getting it. For translation equilibrium, plus or minus F1 minus F2 equals to 0. How?
Okay. So what you are unable to understand? Sorry. Yes.
So that's yellow part for translation equilibrium.
Sigma Fx equals to 0, sigma Fy equals to 0, sigma Fz is equals to 0.
So that one is clear, but the thing that was written under that.
Equals to 0, yes. This thing, this equation you have not understood. R minus F1 minus F2.
Yes, sir.
Okay. See, this is my rod. Only write the upward or downward forces. Only forces. How many forces? Upward, downward, right, left, any direction. Write all the forces which are there in the figure. This is the one force which is make a free body diagram. Okay. This is R. Okay. And
yes, sir.
This is F1. Okay. And this is F2. Okay. This rod is in equilibrium, complete equilibrium. It is not moving anywhere. It is like you have placed a pen on the table. It's in equilibrium. Okay. So equilibrium, there is translational equilibrium. So translation equilibrium means, see, the forces are only along the y direction. There is no force along the x-axis or the z-axis. So they are already 0. So it means Fy is, sigma Fy is equals to 0. Right? What is sigma Fy? Add all the forces. So like upward direction I am taking positive, and downward direction I am taking negative. Yes?
Yes, sir.
So this is now sigma Fy I am writing this thing. So plus R minus F1 minus F2 is equals to 0. See, I am using the sign plus and minus. So I am taking the effect of direction. Okay. See, if
Sir, we'll consider the weight of the support also.
Let me write it again. Yes, good question. R plus F1 plus F2 is equals to 0. Yes, this is what is the meaning of the net forces. Yes, agreed.
Yes, sir.
Now what is this R vector? Its magnitude is R, and direction, if I have only two direction, I can write it with plus and minus. See, I have removed the vector sign. Okay, so direction and magnitude. So this is the direction, negative direction, and this is the magnitude R. Now F1, This is the magnitude. What is the direction? Minus. So the direction is a minus. So minus F1. Okay. Now similarly here, the magnitude is F2. What is the direction? Downward, which is negative. So minus F. And that is equals to, what is the magnitude of this? 0. Z0. Is this clear? This is positive R. This is the direction is positive for R. And for direction of F1 and F2 is negative. Now what was your question?
So will we consider the weight of the support also?
No. Why? See, this support is there on the ground. This is the ground. Okay. Support is there on the ground. It is not in air. Okay.
So sir, from our force
Where do you
come.
place the support? Obviously, you place the support on the ground to lift the load. Yes. Yes. Mansi, is your doubt clear?
Yes, sir.
See, that's a very. See, you are asking a good question. Let me. This is a very. This doubt comes often in our mind. See, free body diagram. I am drawing the free body diagram of the force acting on the rod. I am not talking about the force acting on the support. Okay? Because if you write the force acting on the support, it will also be R. So the net will be 0. Net will be cancelled out. So that is why it is in equilibrium. But now what you are studying? You are studying the forces on the rod. Forces on the rod. Forces on the body. That is what you are drawing, na? You are not drawing the force on the support. Yes?
Yes, sir.
So don't get confused. There will always be two forces, but which force you want to take? You want to take the force on the. If you want to take both the forces, it means you are studying the system, and this system has two things: this lever and the support, and they are in equilibrium. So it means support. Both of them are applying equal and opposite forces. So the net force on the system is 0. It is not moving. And now if you are talking about the forces on the road. So only the forces acting on the road. So like see, this force is acted by the load. So obviously it is also acting opposite direction, force on the load also. This is the effort, force by the effort. This is the force by support, the normal action due to support. Got it? Obviously there will be equal and opposite reactions, but we are not taking the reactions. We are taking only the forces acting on the road. We are not taking the reactions. Of course, we are taking the force only. Have you got the concept?
Yes, sir.
Otherwise they will cancel out. Okay, that is written in the NCERT book also. Don't take both the forces when you study Newton's third law. It is clearly written that students often get confused when they take both the forces. So especially that is why they have written in the NCERT. You can read it over there. Newton's third law of motion. There is this line written over there. Shall I tell you this line? Open page 97. Because these two forces will be, because if you are studying the force on the support and this lever, so then it will be a system. And the forces acting in a system, if you are taking this whole as a system, what your system has? What your system has? Load, rod, support, and effort. These four things form your system. Okay? So the internal forces, the sum of internal forces will always be 0. What is the meaning of internal force? Internal force means force between 1 and 2. If this is 1, 2, 3, 4. Force between 1 and 2 plus force between 1 and 3 plus force between 1 and 4 plus now similarly force on 2 due to 1 plus force on 2 due to 3 plus force on 2 due to 4 plus similarly we will write for third also, so the net will be 0. Okay, because F12 is equals to minus F21, so net internal force will be 0 because F12 will be equal and opposite to F21, isn't it? Here if this is R, this will also be R, that is equals to mg, whatever the mass of the rod is. So same is the normal reaction, same is the R. Beta, have you got it? Don't get confused. Are you talking about the system or are you talking about the forces on the road? So if we are talking about system, all the forces will cancel out each other, okay? Yes?
Yes, I got it.
See, page 97, second column, last paragraph. However, if you are considering the system of the two bodies, if you are considering the system of the two bodies, then FAB and FBA are internal force of the system. फिर तो वो internal forces बन जाएंगी ना?
Yes, sir.
So if you are talking about external forces on the road, so your system is road only now. Okay, not the other things. So what are the systems acting on the road? Got it?
Yes, sir.
So we are not taking this force. Okay. Now Veena, you were also asking one question.
No, sir, clear.
Okay. Now if we talk about, make this figure and write the translation equilibrium if you get confused. Now make another figure for the rotational equilibrium. So there is rotational equilibrium. Okay. Now tell me the forces. You have to write all the forces. So this is R, this is F1, and this is F2. These are the three forces. Okay, and this is the distance from the origin I need to take. So this distance is D1, perpendicular distance. This is D2. And how much is the distance? If any force is acting over here at R, then here torque is 0. Why? Because R is equals to 0. So for R at O, tau will be 0. Yes, why? अरे perpendicular distance तो 0 है. Yeah. Will there be any torque due to R at O?
No, sir.
Why?
So, because the angle between them is 180 or 0.
See, the length is 0. See how you are applying the force. This is the point of application of force. Yes, and this is the distance. So what is the distance between the origin and the point of application of force?
0.
0. What is the distance here between the point of application of force and origin?
D1.
What is the distance here from the point of application of the force and origin? Point of application of force and origin? D2. What is the distance here in case of point of application of R and origin?
0.
0. So if you want to write, you can write. There is no problem with it. So rotational equilibrium. So net tau in z direction, because these are in x and y direction. So this distance is in x direction. Means along the x-axis, and your force are along the y-axis. So obviously the tau will be along the z axis, right? Perpendicular to the direction, perpendicular to the plane containing r and f. So tau z will be 0. Okay, so tau z is 0 means what? This means so start from here. F1 D1. So what kind of force will be there? It is pressed down, so of course it will move in this direction. So that's positive direction, and you are moving it down. So here the direction will be negative. Yes. So here what is the torque? Plus D1 F1. What is the torque due to R? Plus 0 into R, I can write, plus due to F2. Now what is the direction here?
Downward.
Downward.
Yes.
So minus d2 F2, and the net will be net torque is, this is the net torque, so net torque is 0. Okay, is this clear to everyone? So you need not to write 0 into R. Okay, if you want to write, it's better if you write. So
force is acting downward, so it will be negative now. Everyone.
no. So see, no. What is the direction of rotation? I am taking
Okay,
tau
sir.
here. Tau. Direction of rotation will be here. If you are in this direction, so the rod will come rotate like this, na? Due to this F2.
Yes, sir.
Yes. And from here, if you are applying the force, so it will move in this direction. This A will come down. A will come down, na? If you are applying the force F1, where A will go? Tell me, where is A will go?
So downward.
Downward. It is, we have a support over here. If there is no support, then it will come vertically downward. I have a support over here, so there will be rotational motion. Okay, but here it
Yes,
is
sir,
in
got it.
equilibrium, right? And if I pressing F2, so like you are picking this load up, so obviously this will, B will come down and it will be rotation. Is this okay?
Yes, sir.
So the means anti-clockwise direction I am taking as positive, and clockwise direction of the moment I am taking as negative. So this D2 F2 will go that side, and I get D1 F1 is equals to D2 F2. So that's the relation I have derived, principle of moments. Is this clear? Now I can write it as load arm into load is equals to effort arm into effort, and this equation I can further write as mechanical advantage is equals to F1 upon F2 is equals to D1 upon D2. Okay students, I hope it is clear to everyone.
Yes, sir.
Okay, I will also upload this video.